In today's video, we are going to discuss about the equivalent circuit of an operational amplifier. We will see the AC analysis, DC analysis and different kinds of the gains associated with this. Generally with one transducer or one system, we have only one system gain. But in the case of operational amplifiers, we have two gains. One is the differential gain and the next is the common mode gain. We will be looking at both of them in this video. For a basic idea about an op-amp, you can go to my first video where I've just discussed what an op-amp is and some few questions which everyone will have in their mind with respect to operational amplifiers. In this video, we'll discuss only about the differential amplifiers equivalent circuit and the equations associated with this. Okay, so let's get started. Before we proceed with the DC analysis, we'll first understand one concept of this equivalent circuit. Why are we separately analyzing the AC and the DC part separately? Because it is going to coexist. Like I said in my first video, we have the operating circuitry based out of a DC supply, which is this plus VCC, and we have an AC input supply which is applied to the input and the input non-inverting and the inverting terminals, which is supposed to be amplifying the difference part and suppressing the common signal. Okay, so we have two signals over here. One is the supply input and the operating input. Operating input is the DC and the supply is the AC part. Okay, so we are analyzing both of them separately because both of them are designed for different purposes and we are applying superposition theorem over here. How? We are first suppressing the AC part because AC part is applied to the transistor's base, right? This and that. This is the inverting terminal, that is the non-inverting terminal, and these inputs will be AC. To analyze the DC alone separately, we are having only this DC supplies and we are nullifying the AC supplies for now, so that we will understand the DC's circuitry and then go ahead with the AC part. Okay, so before we proceed with this video, I have one small question for you. Amplifier, what is the purpose of an amplifier? I am talking at, let us say, 2 decibel. Okay, when you are hearing that, you will be hearing it at 4, 6, 8, 10 and etc. because you have the volume control in your mobile phone or in your device that you are viewing. You are using the volume buttons to amplify my voice, right? So how is that really happening? Is law of power conservation valid here? Yes, law of power conservation is valid everywhere, but in this circuit, we need to think a little bit more to understand how law of power conservation is holding good. Okay, so having the law of conservation part aside, let us first analyze the circuit and later on I will explain you how law of power conservation is applicable over here. Okay, so in the DC analysis, we are applying the plus VCC to the collector inputs of both the matched BJTs or MOSFETs, whatever. Why should they be matched? Look at this video. Okay, so when we say that these two transistors are matched, we mean that the internal resistance Ri1 of this is same as that of the second Ri2, which is same as the beta Re. Okay, and another thing is the collector's current is equal to the emitter's current divided by 2. This relation holds good here. Okay, so just to ensure that both these are holding good, we are having both the BJTs to be matched. Okay, so when we are applying a voltage, a collector current IC flows here and the collector's current IC2. IC1, IC2, both of them flow here, right? So we are taking the output from this terminal. Okay, this is VO on and this is the second input VO2. So what is the voltage at this terminal? This part minus the voltage drop across RC, right? So VO1 is equal to VCC minus IC into RC. So VCC we know we are going to supply, RC we know, we have designed the circuit. What is IC? To find out IC, we either need to find out IE or IB. Since we have nullified this, there is 0 volt here and there is a drop of 0.7 across the base emitter junction of a silicon diode. If it is germanium, it is 0.8. Okay, so generally silicon transistors are used, so we are considering this to be 0.7 volts. Okay, so what is the voltage at this point? This is equal to minus 0.7. Okay, so let us find out the emitter current and hence find out IC. Okay, so what is the emitter current? The voltage drop across the emitter resistor, this is RE. Okay, so the voltage drop across this resistor divided by RE will give me the current IE, right? What is IE? IE is equal to VE, which is minus 0.7 minus VEE, right? Because the current direction is from VE to minus VEE, so we are presuming that this is the higher voltage. Yes, it is the higher voltage. Okay, so the higher voltage minus the lower voltage divided by the resistance through this path. Okay, so this is equal to this voltage difference divided by RE. Okay, so we will slightly rearrange and get minus of minus is plus. So this is VEE minus 0.7. VEE minus 0.7 divided by RE will give the value of the current IE. Okay, so what is IC? IE divided by 2, right? Is equal to VCC minus IE divided by 2 into the value of RC. So this will give me the DC output. Okay, so to the final output, we have a superimposition of the DC value plus the AC value. Okay, the AC value is like a controlling current and the DC value will set the level of this current. Thus, the amplification happens. Okay, this is equivalent to this circuit where we have a small resistor connected to a DC supply and where the IC acts as a control AC output. The value of the DC is controlled by this AC. So as a result, we get an amplified output. Okay, so this is the DC analysis of operational amplifier. This is the output that is occurring purely because of DC. When we have 0 volt connected to both these terminals, this will be the output and this output is because of DC supply. Okay, this DC operating supply. Okay, so I'll just clear the screen and we'll analyze the circuit with respect to the AC parameters. So when we are analyzing it with respect to AC parameters, we need to draw the AC equivalent circuit where this base part will be replaced by the base resistance and a current source which is beta RE. Okay, so I'll clear this and we'll now see the AC analysis. In the AC analysis of this circuit, we have applied the AC voltage across one of the terminals and we have connected the other one to the ground. Okay, and we do not have any operating circuitry over here. We are considering the output VO1 and VO2 purely because of the applied AC input signal. Okay, so it doesn't mean that we are not going to supply any voltage for operational, but for applying superposition theorem, we are not considering the DC part for now. We are considering only the AC voltage which is VI1 and we are seeing the effect of VI1 over this point. Okay, since we have understood one point that this transistor and this transistor is matched, the beta RE term is same, the internal resistance Ri is same as here and this will also make the current IB1 same as the current IB2. Okay, we are considering ideal scenarios over here. So the value of Re tends to infinity. Ideally, we do not have any resistance called as infinite resistance. We just mean that this is an insulator. Insulators also have resistance. It will be really high. It will be in the order of 10 power 12 ohms or something like that. Okay, we can imagine that this part is an insulator for now. Okay. So, when this part is an insulator and we are considering an ideal circuit, we establish a current path like this. IB, imagine that IB1, okay, this flows here, flows through RI1, and since this is an insulator, no current flows through this, okay. So, this current will travel upwards towards RI1 and end into the ground. We are considering this loop and let us apply KVL over here. Okay, so by applying KVL, okay, the path is only through RI1 in series with RI1. So we have two resistances of value Ri which are in series. So what is the value of the current IB1? IB1 will be the voltage across these points, which is VI1 divided by 2 times Ri. Okay, so this is the value of the current IB1. So what is the collector current? The collector current is this current, right? So what is the collector current? IC1 is equal to beta times IB. Beta is the current gain, which is IC divided by IB. So what is, okay, I'll write it here. Beta is the current gain, which is IC divided by IB. Okay, so what is IC? Beta into IB. So IC1 is equal to beta into IB. What is IB? This. VI1 divided by 2RI. Okay, so this is the value of the collector current. So what is the output voltage VO1? VO1 is the voltage across this RC. Okay, so it is IC1 times RC. VO1 is equal to IC multiplied by RC, which is equal to beta into this. So by the concept of matched transistors, we know one thing. Beta Re will be same as the internal resistance of this transistor Ri, which is same as Ri1, which is same as Ri2. So let us replace this by this. Okay, we will replace this term by beta Re. Why? Since we have a beta on the numerator, we want to cancel this current gain and prove one small point here. So we will replace this Ri as beta into Re. So beta beta cancels. So VO1, I will continue writing here. VO1 is equal to VI1 divided by 2Re multiplied by Rc. So this output depends on the resistor Re and the input voltage and of course the resistance value of this collector. We do not have current gain in this picture. So we are proving one point that the gain of the transistor because of AC part doesn't depend on the current gain of the transistors. It is device independent. Every transistor will have a current gain beta. So it is proved that the AC part doesn't get affected because of the current gain of the transistor. However, it depends on the value of Re. So what is the value of the gain? AB. This is VO1 divided by Vi. So this is equal to, if this Vi comes in the denominator, we will get Rc divided by twice Re. Okay. So this is the AC part current gain, or this is the current gain because of the AC signal, and this signal is applied only to one terminal. What will happen if we apply another value of Vi1 over here? What will happen? The current gain will be, I will write it here. I will write it as AV2. AV2 will be 2 times this, which is nothing but Rc divided by Re. Okay. So if we have another AC supply here and AC supply there, this will be the current gain, and if we have only one source, this will be the current gain. So now we have seen three things. We saw the DC analysis part, where we saw only the operation of the difference amplifier because of the operating voltage plus VCC and minus VEE. Now we saw the differential gain, which means there is a differential input and output. Consider that this is 0 volt, okay. So we have applied differential input and we have considered the differential output. So this is the differential gain of this op-amp. How to find out the common mode gain? Common mode signal is applied to this transistor, meaning that the same voltage will be applied there, okay. It is just one loop. The same VI is looped back to the second terminal also. That is when we call it as common mode signal. This is not connected to ground. The second transistor or the inverting input is also connected to the same VI, okay. So we will have IB because of this transistor, IB1 because of this, and another IB will be here, and both of them will get added and move into the resistor RE, okay. This is IE. What is IE? Base current plus the collector current by general definition of a transistor, right. So what is this IE1? IE1 will be IC1, this collector's current, plus the base current of this. So what is IE2? IE2 will be this collector's current plus the base current of this, okay. I will rub everything, and now we will see the common mode gain. We saw the differential gain now. Now we will see what is the value of common mode gain. So what is the effective value of this? This plus this, right? First, what is IE1? Same will be the value of IE2 because we have connected the same input to that terminal also. So this will be beta into IB1 plus IB1, right? So what is IE1? I hope everyone knows this as a formula. Beta plus 1 into IB, that is beta plus 1 into the base current will give you the emitter current, okay. So this is value of IE1. So the same current will be here. So this will be this multiplied by 2. So this will be 2 into beta plus 1 into IB, okay. I am just writing it as IB because these are matched transistors and the same base current will be flowing through both these transistors, okay. So what is the emitter current? 2 times beta plus 1 into IB, okay. So now let us find out the value of differential output VO1, sorry, common mode output VO1 and VO2, okay. So what is this? The voltage across this is VO1. What is this voltage? The collector's current multiplied by RC, right? We need to find out the value of IB. So when we find out IB, we can find out IE, and from this we can find out the value of output, okay. So what is IB? IB is the current that is flowing here, right? So what is IB? IB will be the voltage divided by the resistance Ri, this part, the current contributed by this, minus this part, which is 2 times beta plus 1 into Re divided by Ri multiplied by IB, okay. So let us take the value of IB to one side and we will get IB into 1 plus 2 times beta plus 1 into Re divided by Ri. So this is equal to the input voltage divided by the resistance Ri, okay. So we will simplify and find out the value of IB, okay. So to have this term alone, we will isolate IB and put all others to the other side. Okay, from here I am continuing here. So what is the value of IB? IB will be VI divided by Ri whole divided by this term, which is Ri, I am just taking LCM. I am putting 1 as Ri by Ri. So that Ri plus 2 into beta plus 1 Re whole divided by small ri. Okay, I am putting this big term to this denominator. So these two ri's will cancel. So Ib will be Vi divided by this term. Ri and Ri is getting cancelled. Okay, so this is the value of the base current. So once we found out the base current, we can find out the value of collector current and find out VO1. What is collector's current? IC is equal to beta into IB, right? So this term into beta. Okay, so this is the value of the collector's current, and now if you substitute the value of IC over here, you will get the value of VO1. Okay, I'll rub this. So VO1 will be the collector's current, which is beta into Vi by Ri plus 2 into beta plus 1 into Re multiplied by Rc. So what is the gain? The gain will be the output voltage divided by the input. So the gain, I'll put it as AV dash. This is the common mode gain because we have applied the common signal to both the terminals. The common mode gain will be beta into Rc divided by Ri plus 2 beta plus 1 into Re. So this is the value of common mode gain. In this video, we saw the circuits of the DC analysis and AC analysis separately, and within AC analysis, we understood the differential configuration and common mode configuration. The OPAMP will have very high differential gain and very less common mode gain. And this factor is explained by the value of common mode rejection ratio. What is the purpose of OPAMP? If you apply both inverting and non-inverting inputs, it will amplify the difference and suppress the common signal. Imagine that you have two signals which has the same noise. Both these signals are applied to the inverting and non-inverting input of an OPAMP. Okay, so both these have the same noise, and since it will suppress the common signal, the common noise which is common to both these inputs will get suppressed and it provides a good output which is amplified. Okay, this is the main objective of an operational amplifier. So the differential gain should be very high and the common mode gain should be very low. It should be 0 ideally, but it will not be 0. It will be somewhere close to 0.5, 0.6 or something like that. Okay, so how to nullify this thing? That is where the ratio, common mode rejection ratio, comes into picture. In the data sheet of an operational amplifier, you will find this value. That is, to the common pin of the OPAMP IC741 or any operational amplifier IC, there will be a terminal where we have to supply some voltage to suppress the common signal. Say for example, you are applying the same signal, same AC signal to the inverting and non-inverting inputs. Ideally, the output from that output pin, it's supposed to be 0 because we are applying same signals. But practically speaking, this will not be 0. This is due to the operating DC supply that's present. Okay, so the common mode rejection ratio defines the ratio of differential gain to that of common mode gain. Okay, that is what is CMRR or common mode rejection ratio. So what voltage should you apply to this OPAMP to make this 0? Let us say for example you are getting a common mode voltage of 0.5 volt. Okay, so if you supply this 0.5 volt to the common mode pin of your IC, this will nullify the effect, and it is almost as if the common mode output is completely zero. So you have totally suppressed the common signal and you have amplified the differential signal. Okay, so we have seen the derivations for the differential gain and common mode gain in this video. Thanks for watching. If you have any doubts, do let me know in the comment section, because in many books I've observed that these derivations will not be explained fully. It will not be taken care step by step. You will suddenly see one step and they'll be jumping to the another step. If you have such confusions, do take a picture of that derivation and send to learningtoengineer@gmail.com, or you can just let me know in the comment section. Thanks for watching. Subscribe my channel for more videos on similar content, and in the next consecutive videos I'll be uploading more on operational amplifiers and some questions which is asked by students. Thank you.